In this lecture, we will be looking at an advanced version of the limit comparison test for the divergence of infinite series. So recall the fundamental question for series convergence when we have a sum of non-negative a sub n's and going from 1 to infinity. Does this sum converge or diverge? Is this a finite sum? And every convergence test that we look at in trying to decide whether a series converges or not boils down to the question of, do the terms a sub n, do the terms we're adding up, approach zero at a fast enough rate as n goes to infinity for the sum to be finite? And that idea will be illustrated in this version of the limit comparison test for divergence. So suppose we have two series of non-negative terms. We have a sub n and b sub n. And suppose that the limit as n goes to infinity of the ratio of the terms a sub n over b sub n as a sequence is infinite. And further, that the sum of the b sub n's diverges. Then the sum of the a sub n also diverges. So first of all, let's think about it in the context of the idea that for a sum to converge, the terms have to race to zero fast enough. Here we're saying that the sum of the b sub n's diverges. If it diverges, it means the b sub n go to zero too slowly or not at all. Maybe they have a limit other than zero. Think like the nth term test. One of these two is the case. So the sum of the b sub n's diverges. For the context of this test, it will be more intuitive if we focus on the case where the b sub n go to zero too slowly. That's going to be the more natural way to think of this. So if the b sub n go to zero too slowly, but they do go to zero. So in that case, the b sub n in the denominator of this limit of the sequence is going to zero. But for this overall limit to be infinite, the a sub n is either not going to zero or is going to zero even more slowly. So again, let's think about the case where both of these are actually going to zero. And they're going to zero at too slow a rate. So if b sub n is going to zero, but too slowly, so that the sum of the b sub n's is infinite, and this limit is infinite, it means that a sub n is going to zero even more slowly. So b sub n is going to zero, a sub n is going to zero at a much slower rate to result in this limit being infinite. So again, think of this as a race to zero. B sub n is going to zero slowly, and a sub n even more slowly for this limit to be infinite. Well, if a sub n's are going to zero even more slowly than the b sub n's, then there's no way the sum of the a sub n's could be finite. That's the spirit of this test. Because of this race, you have like a race of two slowpokes. The term in the denominator is going to zero just too slowly. The term in the numerator is going to zero even more slowly, resulting in this infinite limit. So, to illustrate it again, we can think of it as these b sub n's let's assume, again, to make this simpler, let's assume that the b sub n's go to zero and the a sub n's go to zero as n goes to infinity. just to understand the test. So here, in that case, we're saying the b sub n's go to 0 too slowly. And the limit as n goes to infinity of a sub n over b sub n being infinite ensures that these a sub n are going to 0 even more slowly than the b sub n. So as you move down the line here, these b sub n's are getting smaller and smaller, but they're not getting smaller fast enough to have the sum be finite. And because of this limit condition, these a sub n's are getting smaller and smaller, but it's happening even more slowly than the b sub n's. And so there's just no chance that the a sub n's, the sum of the a sub n's, can be finite. So that's the idea behind this test. And let's see an example where we can use this. In one example here, we have the sum from n equals 2 to infinity of 1 over the natural log of n squared. Notice we start at 2, so we don't have a 0 in the denominator. Well, looking at this, we think about the natural log of n. If we draw the graph of y equals natural log of x, we get something like this, and we know if we plug in the natural numbers, well, we get the terms from our sequence if it were 1 over a natural log of n. But we have 1 over natural log of n squared. So I'm going to restart this. Consider the example, sum n going from 2 to infinity of 1 over natural log of n squared. We start the sum at 2. We note that if we started at 1, we would have a 0 in the denominator because natural log of 1 is 0. And let's try and think about what this series might be doing. And let's think about the natural log. If we look at the graph of y equals natural log of x, and we evaluate it at the natural numbers, we can get a sense of what is happening with the natural log of n as n goes to infinity. And if we compare that to, say, y equals x, and we evaluate at the natural numbers, we would get something that looks like this. And it's important to recognize 1 over n goes to 0 too slowly for the sum n equal 2 to infinity of 1 over n to converge. We know that this is the famous divergent harmonic series. Well, if 1 over n is going to 0 too slowly, because the natural log of x takes its sweet time, or the natural log of n takes its sweet time to go to infinity, when we square it, does the denominator here go to infinity fast enough so that the term 1 over the natural log of n squared is going to 0 quick enough for this series to converge? Let's find out. And a natural suspicion is that natural log of n really takes its time to go to infinity. If you ever want to do an experiment with that, take a calculator and put really big numbers in and take the natural log, and you'll be shocked at just how small the result is. So we're going to conjecture that because the natural log of n takes its sweet time going to infinity, and so its square probably does too, these terms just don't go to 0 fast enough for this to converge. That's going to be our guess. So we're going to guess that this diverges. And of course, with these types of questions, when you use a comparison test, you have to guess right for the test to work. And if we guess it diverges, and we think about 1 over n, the sum from n goes from 2 to infinity of 1 over n, to compare this to, that's the classical divergent series. So let's try limit comparison with it. So let's try the limit as n goes to infinity of our a sub n over b sub n, where our a sub n come from our given series and our b sub n is 1 over n, and see what happens. So in that case, we have the limit as n goes to infinity of 1 over natural log of n squared divided by 1 over n. This becomes the limit as n goes to infinity of 1 over the natural log of n quantity squared times n. And now we need to think about this as a race situation. So we have the limit as n goes to infinity of natural log n squared in the denominator and n in the numerator. And this yields an indeterminate form of infinity over infinity if we tried to directly evaluate the numerator and the denominator, which means we can use L'Hopital's rule. Thinking of this as a continuous function or differentiable function n and a differentiable function ln n, for n being real numbers. So an application of L'Hopital's rule says this is the limit as n goes to infinity of the derivative of the top with respect to n would be 1, and the derivative of the bottom with respect to n would be, using the chain rule, 2 times the inside, leaving it alone, to the 1. So 2 natural log of n to the 1 times the derivative of what's inside the parentheses, which would be 1 over n. So this becomes the limit as n goes to infinity of n over 2 times natural log of n. And we see this is again eligible for use of L'Hopital's rule. We know who wins this. We know n wins this because n races to infinity faster than the natural log of n. We know it in the picture. We've looked at this when we learn. This is a classic race that you learn when you learn indeterminate forms in L'Hopital's rule, but we can work it out again. So per L'Hopital's rule, this is the limit as n goes to infinity. The derivative of the top with respect to n is 1. The derivative of the bottom with respect to n is 2 times 1 over n. So this becomes the limit as n goes to infinity of n over 2, which we know is infinite. So we have now established that we have the harmonic series, which diverges, and the limit as n goes to infinity of the ratio of the terms from our series to the terms from that harmonic series. That limit is infinite, and thus, per this version of the limit comparison test, our given series must diverge. And again, the idea is that the denominator is going to 0, but it's going to 0 too slowly. And the numerator is going to 0 even more slowly. And so the sum of that 1 over ln of n squared term must also diverge.